Good day, everybody. My name is John Kearney, and I'll be moderating today's webinar. I want to welcome everyone to our webinar today on introducing the AMETEK Severe Service Probe, which is going to be presented by Michael Gara and Rod Mertz. We're definitely excited to share some interesting information and educational details on sampling and how to improve reliability. Before I turn the presentation over to Rod and Michael to introduce themselves and start sharing their content, I just want to cover a few logistic items with everybody first. We are recording this session, so everyone should be in mute, listen-only mode, but just in case there is any issues, to minimize the background noise, just make sure your phone or your computer mic is muted. We do want the session to be as interactive as possible and encourage you to use the chat feature to ask questions. For those who may not be familiar with the Teams platform, on the top right-hand portion of your screen, there's a small icon there that looks a little bit like a quotation. You can click on that, and the chat box here on the right-hand side of your screen. Feel free to type your questions in there in the chat, and we'll have the speakers either address the questions live during the session, or for more detailed or individual type questions, we may contact you after the session by email to get into those details. As I mentioned, the webinar is being recorded, and it will be available on the AMETEK Process Instruments YouTube page. I did include the link in the chat already, and I'll make mention of that at the end as well. Just for reference, this webinar is sponsored by AMETEK Process Instruments. We are a worldwide manufacturer of process analyzers and instrumentation, and we serve a wide range of markets from environmental monitoring to hydrocarbon processing, including areas like refining and petrochemicals. We also cover power generation, natural gas, and many other industries. Our engineering and manufacturing activities take place at 3 different facilities that we have here in North America, but we do have direct sales and service offices located around the globe, and we are supported by a wide range of factory-trained manufacturer representatives and distributors and service technicians so that we can provide very responsive and local support and service to our end users. So with that, Michael and Rod, I'll turn the presentation over to both of you.
Good morning. Thanks, John.
Hey, everybody.
Michael, I'll give you the first opening salvo here.
Hey, so just real quick, my name's Michael Gora. I think I've met quite a few of the attendees on here. I am a product manager with AMETEK Process Instruments Groups, and I have the responsibility for the photometric line, which includes our SRU, or Sulfur Recovery Unit solutions.
And I'm Rod Mertz. I'm the Regional Sales Manager for Canada with AMETEK Process Instruments. We're going to talk today about a new introduction for the AMETEK SEMS family, and this is the Severe Service Probe. Michael?
Yeah, so I think probably the first question for most people is, what is the Severe Service Probe? So that's where we'll start everything. Rod and I are going to divide this presentation up. Rod will take roughly the first 10, 12 slides. I'll jump in, and then him and I will come back together at the end. But again, we're going to walk through what the Severe Service Probe is. We are going to kind of provide an overview on why SIMS measurements can be difficult in SRUs, and kind of go through the importance of maintaining proper temperature and keeping the sample as representative as possible. We'll get into some details about the probe itself, and then we are going to walk through a blowback process that's incorporated into this system. And that, again, helps keep a representative sample flowing to the analyzer for analysis. Then we'll talk a little bit about the controller aspect of this system, and then we'll wrap it up for any questions at the end.
All right, so what is the Severe Service Probe, or as we're going to shorten it, the SSP? It's a precision high temperature probe system, and what we've designed it for is really those tough high dew point applications where you have a lot of probability of condensing out. In most examples that we're going to use, we're going to talk about sulfur trioxide, or SO2, condensing out in high SO2 concentrations. The probe itself is a cooperative effort between us and our AMETEK sister business unit, Universal Analyzers. And what we were looking for was to produce something that was an effective solution for applications, like we said, that have these high dew point samples that typically have been very problematic. And we're going to show some examples of some of those problems that we've come across. It's specifically designed to work with our AMETEK 909, 910, 919, and 920 analyzers. The applications that we really think should be considered for the SSP are sulfur recovery units, the incinerators and sulfur recovery units for both refinery and natural gas applications, sulfuric acid production, and other high dew point applications that could be considered suitable. So sulfur trioxide and acid dew points are very problematic in the SEMS world for especially something like a sulfur recovery unit where you don't have, let's say, the most efficient tail gas treating unit on the back end of it. And what happens is in high concentrations of sulfur dioxide, roughly 1 to 3% of the concentration of sulfur dioxide will convert over to sulfur trioxide in the presence of heat and excess air. This reaction will be catalyzed further towards the SO3 side of things if there's a lot of metals such as catalyst fines present. And depending on the process, that's not terribly uncommon. So again, the factors that increase the amount of sulfur trioxide, high temperature combustion, high sulfur content, excess oxygen, and the availability of catalyst fines. So as we mentioned, anywhere from 1 to 10% of the SO2 concentration, and we average around 2 to 3%, can be in the sulfur trioxide form. Just to give you kind of an example, and this data comes from sulfur experts who was very kind to share their slides with us. At roughly 200 to 300 ppm SO2, you're going to see approximately 10 ppm SO3. That's a dew point of about 90 degrees C. So what happens is sulfur trioxide will combine with water on surfaces when it hits the dew point and form sulfuric acid, so H2SO4. And this is a severe corrosion product, essentially, of this combustion process, and it will cause all sorts of problems with your wetted sample lines, the analyzer itself. And as we increase in concentration of SO2, you can see that the dew point rapidly goes up. So from 10 ppm to 100 ppm, we go from a 90 degree C dew point to 150 degree C dew point. At 1,000 ppm SO3, which is basically 2 to 3% SO2, we're sitting at a dew point of about 205 degrees Celsius. Now, most applications will not run that high in an incinerator type application. Typically, in the modern age of, for example, sulfur recovery units, their efficiency will be well above that and produce below 2 to 3% SO2. So what we find from AMETEK's kind of historical perspective is most customers, or a majority of the applications, typically have a dew point of less than 176 degrees. So what this means is that if you look at the the system, the wetted system for your SIMS analyzer, typically the first cold point that it's going to hit is the probe nozzle, and that's where most of the initial condensation of SO3 ends up happening. Here's some examples of green slime. Now, the upper left-hand corner one isn't from a SIMS unit, but it was a nice picture, so we thought we would show it. So this is SO3 leaching out the nickel and chromium from stainless steel, which causes this greenish, lovely greenish color. Here we have some examples of corrosion from the SO3 combining with water to form H2SO4. So you can see the dramatic pitting on the end of the probe tube here. Basically a completely destroyed zirconia oxygen sensor. And then a probe tube with the pitot tube and RTD, you can just see it's completely covered and corroded. So these are some of the examples of what happens in situations where your dew point is causing the SO3 to drop out on the wetted components. So as I mentioned before, the AMETEK SSP probe head is a joint effort in design with Universal Analyzers and Process Instruments, AMETEK Process Instruments. What we've done is basically taken one of their designs and modified it specifically for these high dew point applications. And it consists of the heated probe itself. I'm hoping that everyone can see my cursor. Just use a highlighter here. So the heated probe itself, sorry, I guess the highlighter doesn't work. We'll use the laser pointer. Here we go. The heated probe itself, the heated probe filter, the accumulators that operate the blowback, and then the solenoid and electrical components, as well as the Z-purge to meet the Class 1 Division 2 area classification. Here's kind of an exploded diagram, bringing them out individually. The heart of it is really the temperature controlled zone. So the heated probe tube assembly, the heated filter, and then the heated box itself. These do 90% of the lifting for the SSP probe, and the other 10% of the lifting is done by the blowback in terms of preventing probe tube fouling. All the wetted components are available in 316. We also offer Hastelloy C276, and I believe there's some high temperature alloy development in the works as well. So here's an internal flow diagram of the SSP probe. I know it's probably tough to see on your smaller computer screens if you're looking at this with a laptop, but just quickly, what we do is we have the two accumulators. One is responsible for the heated filter. One accumulator is responsible for the actual probe itself, for the blowback portion. Again, the first typical cold point problem where we see SO3 condensation is usually in the nozzle where the probe connects to the stack. That's typically the first point of heat integrity loss, if I can use that term. One of the things that in retrofitting an SSP, and we'll talk about this further on in the presentation, but in retrofitting the SSP probe, we do require an instrument airline be run up to the analyzer, and we do recommend anywhere. Typically, we found the sweet spot to be between 90 and 100 psi-G for instrument air to pressurize the accumulators. There are two separate cycles. So as I said, we first blow back the heated filter, we then blow back the heated probe, and this cycle is repeated twice. Typically, the cycle takes about 2 seconds per cycle. And Michael will talk to some extent about how that works with the controller system. Sorry, I keep having to switch screens here to change slides. So the maximum operating temperature is 190 degrees C. This is limited by the T3 rating of the certification, the Div 2 certification. Again, we have dual accumulators for blowback operation. One is dedicated towards the probe filter. One is dedicated towards the probe itself. We do isolate the analyzer during the blowback function. We use a PLC to control the temperature zones for the probe tube, filter, and enclosure. And all three of those zones have the ability to go up to 190 degrees Celsius. There is an optional acid knockout system for higher dew point, things that are higher than 190 degrees C that can be used. Again, we'll want, pretty accurate stream compositions to do the math and see where you fit. Obviously, the less complexity we can build into the system, the less maintenance will be required. So if you can, function without the acid knockout system, we highly recommend that you do so. And as I mentioned before, we do have optional wetted material metallurgies. I'm going to hand it over to Michael to talk about the actual controller portion of the system.
Hey, thanks, Rod. I don't know if you saw my request for control. Were you able to grant me that?
There you go.
Okay. So thanks, Rod. Hopefully everybody on the call agrees that Rod has demonstrated that we have a probe that's capable of generating a representative and maintaining a representative sample through both temperature and flow maintenance. And by flow maintenance, what I'm referring to is keeping the path clear of any particulates that may be getting into the system. And that's accomplished by doing the blowbacks at the filter as well as in the probe. But the logical question, though, and Rod alluded to it when he was walking through the probe's functions, is how is that managed? And the way we manage that is by utilizing what we refer to as our severe service probe controller, SSP probe controller here. And again, I hope you can all see my my mouse. I'm going to move this around a little bit. And essentially, the probe controller just pulls everything together. It's sitting in between the analyzer, the heated sample lines, and the probe that Rod just walked us through. And it's responsible for managing the temperature zones of all the components that Rod mentioned, but also it's working with the analyzer to manage its temperature as well as the heated sample lines. Are some people having an issue seeing the screen right now? Because I think I'm speaking to this slide.
Michael, I can see your screen.
Okay. Okay. In addition to the controlling of the temperature zones, which again, hopefully it was very clear from Rod's walkthrough that's of critical importance is maintaining temperatures above the dew point. We also need a way to drive some of those solenoids that do the back purges and for both the filter as well as the probe, as well as, and again, I hope this was kind of picked up by those on the call, that we need to isolate the sample while we're doing that, those back purges, because we don't want to be shoving instrument air into the analyzer path there during that blowback. We want it all concentrated on the filter that's up in the probe enclosure as well as the probe tube. And then there's one other element to the probe controller, and that's it's monitoring the faults and alarms that may be occurring. Again, it's perfectly normal to have process upset conditions, and sometimes those process upsets can even include some power surges or instrument air getting shut off. And that's the point of having the probe controller, is that it can provide a status update to the users. So I'm going to try and go to the next slide, Rod, and if it won't, okay, whoops, there we go. So The controller components, the real brains behind this is an Allen Bradley Micrologic's programmable logic controller, which is essentially a PLC. And then we tie that to a Allen Bradley panel view HMI. So this is a touchscreen HMI. And I'm going to walk through the various screens that are available on this panel view display here. But we also need to tie back to the analyzer. And that is done via a gateway and an Ethernet switch tying us back to the 909, the 910, the 919, or the 920 analyzer from AMETEK that would be actually measuring the H2S and the SO2. So again, this is the probe controller assembly up here. We've got the touchscreen interface. And again, I'm going to walk through some of the various screens that are available. And then down here, we actually have the heart of the system. What's going on is we have a PLC, and then we've got some interfaces here. And obviously, we're driving various solenoids and sending out other connections, whether they're digital or other IOs are all being driven here inside this enclosure assembly. So again, I'm going to try and keep us moving here. But it is a good size color touchscreen, 9 inches. So it provides a easier way for users to interact both back to the analyzer as well as up to the probe assembly, and not try and do that from the actual analyzer itself. So this is a dedicated screen that users will be able to operate either manual sequences that they can go through, or they can configure it to set up some automatic blowbacks or other automatic events, including auto zero, calibration, or even a validation. It does have an alarm log view. Again, I'll have a slide dedicated to that coming up in a little bit. And then what I think is really slick or neat here is we have the ability to demonstrate what's actually happening in the entire system, from the analyzer all the way up to the probe, through basically an animated PID that will allow users to see exactly what's happening and allow them to actually manipulate various components in that system and to check and ensure everything's working as intended. So I'm going to start with the first screen, and I know a number of questions have been coming in, and I'm not ignoring them. What I'd like to do is get through the actual slides here, and then we'll address the questions at the end. So again, keep the questions coming. Just be patient though, because we may answer some of the questions you're asking, and if we haven't, we'll address them at the end. So the SSP probe controller's home screen is what we're looking at right here. And in it, you can see what the temperatures are at, not only at the probe tube, which Rod was pointing out is so important to maintain that temperature above the dew point there, because we do see a lot of damage occurring to probe tubes and other components on there. So what we do is we keep that temperature, and in this case, 190 C. And from the home screen, the user will be able to see where that temperature is at. They'll also be able to see if there's any issues further downstream. So in the probe filter, as well as in the enclosure, see what those temperatures are at. And then what's always, I find very critically important when I'm looking at an integrated solution is, can I see, are all my components ready? One thing that would drive me nuts is if I'm looking at a screen on one part of an integrated solution, and I can see that it thinks everything's going great, but in reality, in this case, let's say the analyzer is not operating properly. Well, if that were the case, you'd have a message right here. But fortunately, everything in the system is working as it should. So the user is probably getting good results and valid results because the analyzer is not indicating any alarms. The probe, which is being monitored by this PLC controller or probe controller assembly, it indicates that the probe is operating at proper temperatures and there's no alarms there. We're not in any kind of maintenance status, so nobody's gone in there and turned us off and put like a hold current value situation on this assembly yet. And it even monitors whether or not the purge is working properly. So again, if the purge goes out, we would expect to see that the users need to shut down the system because they could be having a situation where they might be violating some requirements of their hazardous area certifications. So from this screen and on many of the subsequent screens, and I'm trying to get an animation to work here. Rod, I don't know if you can advance us here. You'll see right down here, we've got a full bar of, I guess, destinations would be the best way to put it, so that we can move off of this home screen and view some other aspect of the analyzer system, this SSP system, and see how things are operating. So if you can click that again, Rod, another one, we're going to go next to the maintenance overview. And so here's that maintenance overview. And on this screen, you can see what is the status of the actual blowback assembly. You can see where the status is of the various operations of the SSP. An interesting thing to note on here, and I wanted to point this out, is that we can see that there's a sample delay. This is actually counting down. It's at 48 seconds, but it would continue to count down. And what we do is we tell the analyzer to stay in maintenance mode while the sample flow is returned back to the analyzer and through any of the sample handling components after a blowback. And we do that to ensure that the end user doesn't get some random reading of, let's say, 0 H2S and SO2, because effectively all it's seeing is the instrument error that was used to clear the filter and the probe during the blowback. So we purposely introduce a delay there. And that's what you can see here is that we've got a countdown going. From this screen, you can also test your various valves. You can click on here and actuate the solenoids and make sure that they're working again. And you'll see this throughout the screens that we like to repeat what the status of the various components of the SSP are, and that extends itself down to the analyzer controller. Here we also have a indicator that everything's going well with our Modbus communication. So again, this looks like everything's operating as it should. And again, this is the maintenance screen. If we go to the next one, that'll be our analyzer calibration screen. Okay, so from here, an end user can manually initiate an auto zero. They can initiate the validation, or they can initiate a full-blown calibration. And in doing so, these little eggs up here, oval shapes up here, will be highlighted as things are being actuated or not actuated. You can also adjust when you would want your daily auto zeros and validations to occur. And that's what's showing down here. In this case, this will occur at the 2200 hour, so roughly 10 p.m. In the evening. And that's for the zero start. Again, this is about 10:30 or 22:30 in the evening. We'll see the zero start, and then a validation will be running again. A validation is not a calibration; it's just running a known sample through the assembly and ensuring that the analyzer is measuring as intended. Again, it's a test system. No adjustments are made to any of the parameters of the analyzer. Again, manual and auto sequences are both controlled from this calibration stream here, or excuse me, calibration screen here. And the next thing we're going to look at will be the alarm history. So
I just wanted to add in here quickly, this is not a replacement for, your typically mandated DAS controlled system where, you know, your calibrations are set at a specific frequency, blah, 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 blah. This is not a replacement for that. This is specifically for the SSP probe, but it does allow you some flexibility to do things as part of the testing and maintenance procedure. You would not typically run your normal analyzer validation through the SSP probe controller. That would be part of whatever your DAS system is.
Okay, thanks, Rod. Okay, so as I mentioned, the next screen we're looking at will be the alarm log screen. In here, nobody panic. This is some factory testing that was going on, and we were able to generate a number of different alarms here. Some of them are just normal during a startup, where you can see the filter temperature is a little bit low and the enclosure temperature is low. And again, we were generating alarms because once we're sampling, we want to make sure that those components are staying near their set points. And if not, we generate alarms that are viewable to the end user, and we can output alarms from the controller as well. These alarms that pop up here can be acknowledged by clicking down here. That can be done individually, where we go through and the end user would acknowledge each alarm. They may do that because they want to keep something as like a record of that alarm popping up, but they know that it's no longer impacting their measurement. So, excuse me, so they may want to go ahead and acknowledge it. And that effectively allows the system and the analyzer to continue operating as if there are no alarms, but the user can go back and view that alarm in the future if they want to come back and reference it. There is the ability to acknowledge all the alarms. So again, maybe during a startup, when you know that you're going to have a number of alarms here, you can acknowledge all of them, or you could even clear all of them. And so the user can do that here. They can scroll through and view alarms over time here. You can sort the alarms by time, which is what's demonstrated here is that this would have been the most recent alarms were up here, or you can do it by the way we created our alarm messages. They're detailed by location. So you could click on here and sort through and see where am I getting alarms on the probe, where am I possibly having issues with some of my communication. Those are just a couple of examples here. So again, this is the alarm log. Next screen, we're going to be looking at how we can set some of our parameters for the temperatures. And again, you have the set point is right here and here and here for the probe tube, the probe filter, and the probe enclosure respectively. Next to it, the green line is the present value, which is what we're seeing here is the temperatures are running up near that 190 C as they should be. And then you can confirm that down here and looking at the present value is shown right here, as well as the set point is shown right here. And then down below, you can actually see how hard are the individual heaters working. So this is, again, what kind of pull on the heater is occurring in order to maintain the temperature at those various locations. Users can also adjust the alarm settings for all three of those locations. The probe tube, a low temperature alarm can be set as well as a high temperature alarm. Again, this may be, Rod talked earlier about 170 C centigrade is what the vast, dew point is what the vast number of applications that we see in these types of applications is, again, that is the dew point. But maybe the end user in this application, we had done some calculations and it looked at the dew point would be a little bit lower, maybe typically around 160 or 155. So the end user just giving themselves a little bit of wiggle room and setting that low temperature alarm at 165 to kind of catch it before it really becomes an issue for them. So again, set alarms here, and then over here you can view where your different alarms or your different temperatures are running at, and again compare it to what the set points are at for those probe tube, the probe filter, and the probe enclosure. One other item to note here, and again we've seen this on a couple screens and I didn't mention it, is that as you scroll through these different display screens, you will see that we consistently remind the user what the status of the probe assembly, this is a severe service probe, as well as the analyzer are, just so it really jumps out at users. If there's something going wrong with one of the components, they'll be notified as quickly as possible while they're standing there in front of the user interface. Then the final couple of slides I have here, again, I think this is really a highlight. And again, this is, we get to this point by clicking on a navigation box down on a prior screen here. Right here, we would click on the PNID. Thanks, Rod. We get here, and this actually demonstrates what is actually happening with the system while the user is standing in front of the unit. So we can see that right now the probe is in ready mode, the analyzer is in ready mode, they're both in sampling mode. We don't see any alarms or issues here. The sample is coming through the probe and through the heated filter. It's being routed through the heated sample lines all the way to the sample cell. And then it's either being vented out through an aspirator. In this case, it is being vented out or returned to some safe location. And again, Rod mentioned this earlier, our instrument air is filling up these two accumulators and building up pressure, typically around 100 psig is what these are being built up to. And they're storing that pressure in anticipation of doing the blowback. So again, if you can just like do a mental snapshot of what we're seeing here, everything's good to go, and we've got sample running through here, and then the actual blowback assemblies are both turned off. So these sample valves are not energized, so we don't have any of that instrument air coming through. And once a blowback is initiated, you can see that the notification pops up that the probe is in maintenance. The analyzer is no longer reading a sample. It's been because the controller has given it a heads up. And this is actually the second portion. We've probably already gone through. The first accumulator has done its blowback of the heated filter. So that's already shot its 100 psi air through here and started to try and get any particulates that have accumulated on the filter out. The second accumulator is now active. So it's again building off of that first blow from the heated filter accumulator. It's continuing to push particulates back into the process and getting them out of the probe assembly here. You'll note that this third solenoid and actuation valve here has changed status. We are no longer allowing the sample gas to run all the way down to the sample cell. We've actually closed this pathway off, and we're actually running a light instrument air purge through here just to prevent any of this purged particulates that might work their way through here, just prevent them from working their way eventually into the sample path here. So again, we've got a little bit of air going through here, up here, and that's going out here. So again, the ultimate goal here is to clean both the probe tube here and the heated filter right here. Personally, I think this is always wonderful for users to have something like this available to them when they're sitting in front of a user interface on any component, instead of having to pull up drawings or try and locate some drawings that may or may not have shipped with the analyzer when it got installed. Also, in this case, you actually can see how the pathways change based on activities going on, either driven by the user or by some timed event. And again, it makes it very clear which solenoid should be activated and which one should not be, and what the sample pathway is, or what the air actuation pathway is on the system at this point in time.
I do want to add that what's interesting here is you can actually see your analyzer calibration, validation, and zero solenoids and their current state as well. So that's kind of a nice feature. It'll tell you, which solenoid is open when you're in calibration, which solenoid's open when you're zeroing, and which one's open when you're doing a validation.
Yeah, it's a great point, Rod. Thanks. And you know what? I don't have a PNID of that, and I probably should have. Is Rod's indicating that these different solenoids are controlling the zero and the cal and the validation streams here, but then it drives it up to here so that we come back through the sample pathway here. So we are going up to the probe, and we do go through the heated filter when those are occurring. And I think that was a really good point you just made there, Rod, is that that's all controlled here, and you can see those would be actuated or turned off based on the state of the analyzer. So thank you. So my final kind of walkthrough on the probe controller here is just, again, what are the features, and what do we have going on there? And it's not stated here, but hopefully it's obvious that the controller is basically the brains and the heart of the system. It's doing a lot of the thinking and a lot of the processing, and ultimately it's the backbone for providing a status message on a touchscreen interface that's sitting there. It allows the technicians to do various functions and set up different automated features and various settings, including setting alarm points, and even drive the various mechanisms like a zero or a calibration or validation directly from it, and not have to get into the analyzer itself. And again, I think we've talked about a number of these, and I'm getting a little bit concerned about time here. So I'm going to keep going here and kind of pull Rod and I back together here at the end by walking through what are we actually talking about providing with the severe service probe. And everything that's highlighted here in blue, or blue shading, is what we would be providing. And that includes the heated sample line. That includes the controller. I think I saw a question come up, where does the controller reside in this arrangement? And it's going to sit right here, kind of off between the analyzer, which should already exist, whether it's a AMETEK 909 or 910, 919, 920, doesn't really matter. But that analyzer would exist, and then the controller would sit between it and the actual blowback probe assembly, which is going to be mounted on the stack here. And again, all the blue highlighted components would typically be provided. We may or may not need to include a gateway depending on how the original analyzer shipped out. So for customers that are using AMETEK analyzers and are curious and want a quote on this high dew point system or high temperature system here, what we would request is you provide us the serial number of your existing analyzer, and that will allow us to look and see whether or not a gateway exists, so we would know whether or not we need to include that. And then, Rod, do you want to mention anything about the flow? Okay.
Yeah, a couple quick points. Typically, we would integrate the flow sensor and the RTD with the actual heated probe tube portion of the probe. A lot of that will just depend on flange size and nozzle diameter. We can also do it as a separate entity, as is what is shown here. So often this will actually run up here to the actual probe head, and as I said, the pitot tube and the RTD would be integral as part of the probe assembly. The other thing that we want to point out is, the reason why we suggest you replace the sample line is that there's a good probability that your sample line was not designed to run at a maximum temperature of 190 degrees C. So That's the biggest requirement why we would suggest that it be done. If the sample line was designed for that specification, then you could probably get away with it. But to be honest, if you're going to spend the amount of time and effort in putting something like this together, we would suggest you replace the sample line as well. I guess in summary, this is a high dew point specific application. This is not, something you use for your normal everyday, very low dew point applications. We offered the automated blowback of the heated filter and heated probe, the precise temperature control of the probe filter and probe enclosure. It has a live flow schematic of each program sequence and permits manual operation of all the program sequences, as well as manual operation of the individual IOs as well, including all timers and PID parameters. And I think, one of the biggest benefits for most customers is the alarm log view with the timestamp that tells you exactly what's going on, not only with the probe and the controller components, but also with your analyzer. It tells you if you're having problems there as well. John, do you want to go to the questions?
Yep, thanks, Rod and Michael. A good session, and there are a number of questions in the chat. I'll try to group some of them as best I can together, and hopefully I don't miss any. There was a couple of questions on certification. Rod, you mentioned Div 2, but maybe we can knock off a few of the easier ones first. So one question was, is it CE or ATEX certified?
I can't speak to CE. I'm assuming not, but the issue is that this is a universal analyzer / AMETEK Process Instruments hybrid, and at this point, Universal Analyzers only offers it in a Div 2 package. We are in discussions with them, but that's where it is right now. Okay,
and then related to that was a question on CSA, which I assume meant does it have CSA approval, which I don't know if it does on the Div 2.
We get it certified in the Calgary facility by, actually, I think we use Intertek for the certification as opposed to CSA, but it meets the Canadian electrical code, same thing as CSA.
Okay. And then a related question around certification, although probably maybe not directly product related, there was a question about what codes and standards for sample probes should suppliers certify their products to. I think that question was generated around what would a user or EPC need to specify in the codes and the regulation, that kind of a thing.
So for the most part, the probe head itself is sitting up on a stack 100 feet in the air or more. Almost inevitably, but in reality, it is a general purpose application. However, many sites just deem anything within the site as a minimum of Division 2. So to be honest, I would talk to the individual sites. There is no, standard, certainly within the Canadian electrical code, and unfortunately, I can't speak to the American code very much, but it is site specific. So in most applications, this will be a GP, utilized product, but in many applications, just because of, blanket site policies, they'll make it Div 2. Okay.
A couple more questions on the probe, maybe before we go to the controller. One was, has the SSP been used in FCCUs, COKERs, and SRUs in the US? I don't know if we can speak at all to install base.
Not that I'm aware of. I don't know that any have been installed in the US yet, but we're looking for somebody to get one installed at, so I can say yes to that question in the future. So yeah, if you've got somebody that wants to have a discussion about this, we'd be more than happy to.
Okay. All right, and then one other maybe pro question before we get into a number of questions on the controller is, how is a sample pulled into the probe? Eductors, vacuums, pumps, etc.
They use an eductor in the analyzer.
Yeah, if you go back 2 slides, Rod, I think we showed the aspirate. No, we don't. It's a couple more. It's It's on the PNID, one of the last ones I showed. Okay, so yeah, you got it right there. So
Okay.
we're pulling.
Oh, go ahead, Michael. Sorry.
No, I was just saying that we're pulling it through utilizing an aspirator.
All right. I think you answered this one, Michael, because you made reference to it, but you showed where the controller is. We'll switch gears now. The controllers, where the controller is physically located, which I think you showed in one of the last PIDs as well.
So this can be a grade. Just a heads up. It doesn't have to be up at the probe. Doesn't have to be anywhere. You can make it wherever you want. It's just a matter of running, the appropriate cable tray.
Okay. And then I guess somewhat related to location is accessibility. There was a question on, can the controller be accessed and controlled remotely?
You can talk to it. Now, this is getting outside of my area of expertise, but because, it talks all of the communication language of the analyzer, including Modbus, you can do something from the control room if your DCS is set up to talk Modbus and input registers.
Okay. And now there's a number of different questions on some of the, I guess, I call them operational details, I suppose, of the controller itself. So I'll try to walk through a few of these. Can the controller manage more than one SSP probe?
I'm going to say no. And typically, you would have, one analyzer, one probe per system. The controller is designed to manage that probe and talk to that analyzer. So I would say no, I don't think that that's feasible. It's certainly not developed at this point in time, and I don't really see it operating like an AMEVision, where you would have multiple units. Usually there's not a significant number of high dew point sample points that are close together. So I don't think we've ever thought about the need for that, to be honest.
Okay. And I know you guys talked on, Michael and Rod, you both spoke on some of the timing and so on, but I may have missed it myself, but can the frequency of the blowback be adjusted, and is instrument air used for purging?
Yes and yes.
Yeah.
All right. And then there's several questions around temperature and the controller and the probe. So maybe I'll try to group a few of these together. One question was, are temperatures controlled to the set point using electrical tracing on the probe and sample lines and electrical heaters inside filters, controllers, etc.?
So the sample line is actually heat controlled by the analyzer. So the analyzer controls the sample line set point. The probe heater, the probe heater has its own element within the probe itself. The probe filter has its own element within the probe filter. And then if we go back to, where are we here? This photo here, you can see that there's a fin heater that controls the temperature enclosure, as well as a little air bath or sparger device to circulate the air within the enclosure to maintain constant temperature. So there's a heater within the actual filter element, a heater within the heated probe assembly, and then a third heater for the actual enclosure. Sorry, does that answer all the questions, or was there another?
No, I think that covered them. If not, the folks can put in the chat and I'll continue to ask.
Sure.
Another question related to temperature was, if the sample line is 190 degrees C, what is the oven temperature?
Typically the 910, 909, 920, 919 family is 165. The situation is such that we would probably, if you're operating within that band point between 165 and 190 or higher, we would then look at an acid knockout pot, either at the analyzer or down at the, up at the probe head or down at the analyzer. And it would be application specific depending on your particular scenario. We've done both. For customers in the past, there's a an application where we've actually done the acid knockout pot with a little peristaltic pump up at the head, or alternatively, the knockout pot can drain back into the stack. But we've also done it where it's just before the analyzer oven to knock it out because of the lower temperature there.
Okay.
That's a good question, actually.
Yeah. All right. A couple others, I guess, on operation of the controller and sort of some of the logistics. So one is if the controller is near the probe, there's a comment about it, whether or not it'll be convenient for a technician to operate. If it's in a convenient location and you have a bundle of wires to connect, how many wires are needed?
I think that question's best answered if we actually sit down and look at all the features the end user expects to integrate into the solution. I mean, I can't give a set number. Like Rod said, some people will want flow, some won't. But we can work with people. I mean, if we have a specific example, if somebody wants more details on that, we would just want to work through what exactly their expectations are before we give them that final number of wires or bundle size. And building upon that, again, I think we might have went through this too quick earlier. As we're looking at this picture right here, that controller, the severe service probe controller, that could be sitting right in the same enclosure as the analyzer. It doesn't need to be 3 inches away from the blowback probe on top of a stack somewhere. So that there's a lot of flexibility in where that would get located.
Okay, a couple other questions around, I guess, controller operation features. One is, does the controller allow for the analog output hold in the analyzer?
Yes.
Okay, and
So
second
when you select, when you select one of the functions, so let's say you're going to start blowback, it will put the analyzer into maintain last value.
Yep.
And same with the rest of the features.
Okay. And then another one was around, how is the time cycle measurement between two samples, or maybe what is the time cycle measurement between two samples?
I'm not sure I understand the question.
I think what they're asking, Rod, is like, so it does let's say it does a span or it does a zero. How long do we purge the system?
What the cycle time is.
Yeah, how long do we run the next sample through there before we start taking measurements?
Right.
I think it's a minute.
Yeah. Sorry, go ahead, Michael.
No, I think it's 1 minute. I think I might have had that on a slide, or you had it on a slide, Rod. But I think
and it will be somewhat dependent on your individual system, because if you've got 50 feet of sample line versus 150 feet of sample line, your sweep time to get to a T90 concentration in the analyzer oven will be slightly different. So that is programmable within the analyzer parameters.
Okay.
Sorry,
go ahead, Michael.
John, yeah, I just saw a question come in about the PLC box is not being maintained at 190C. Again, Rod, I don't know if you can go to that final schematic. The controller is sitting separate from the actual probe box. When Rod has mentioned the enclosure temperature, and when we showed some of those display screens that were talking about the enclosure, it's referring to Rod, I don't know if can you take your mouse around the blowback assembly? There you go. So that's the enclosure, the heater, and the probe are all right there. That's what we're maintaining at temperature, not the the PLC controller box. We're not keeping that at 190C.
Yeah, it's just this whole upper area that is wetted and needs to be maintained at temperature. So,
okay. We have about a minute left, so let me get one or two more questions in here. Another one just came in. Are there any provisions for automated action on the heater zone alarm / failure, i.e. sample isolation valve or system purge?
I got to look at that question.
Okay, that one just came in from Peter.
So all the solenoids will be definable as whether or not they're in operation from the maintenance screen. I'm not sure, as well as all the alarms. So I'm not sure I understand how to put those two questions together.
Okay, maybe we can address that one offline. And then we're just about on time, so maybe one more here, and then we'll take a look at the list and email anyone that we didn't get to. But one question was, what is the T rating? If there is one.
T3.
T3. Okay. All right. I do want to be respectful of time, although I do appreciate all the terrific questions in the chat throughout the session. Like I said, if we missed anybody, we'll take a look through that list, and if we did miss anyone or any of the questions, we'll make sure that we reach out to you on email and take up their question with you individually. Again, I do want to thank everybody for attending, and in particular, thank both Rod and Michael for an excellent session today, as evidenced by the great questions we had from the audience. I did just post in the chat some useful links on the products, as well as local contact information for those that may want to reach out to their local AMETEK sales representative or distributor for further discussion. And as I did mention at the beginning of the call, we have recorded this session and we will be posting it up on our YouTube page within the next day or so. So again, I appreciate everybody joining today. Hope you found the session informative, and wish everybody a good rest of your day. Thank you.
Thank you.
Thanks, guys.